video, we will be covering how expressions substituted into formulas transform graphs. And these transformations affect all graphs the same way, whether they're some random graph or one of our regular functions from our library of functions. Just a little reminder about our basic functions. We have lines. Lines are non-curved and straight. Their formulas have variables raised only to the first power. So y equals mx plus b, notice y and x are raised only to the first power. But again, you can have the expression written in different forms. Another form, ax plus cy equals d, is a form that you use when you're solving systems of equations. We also have parabolas. Parabolas are polynomials that are of degree 2. And once again, you can have different forms of the formula, completed square, standard, or factored. In an earlier section, we learned other things about parabolas, how every point on the curve is the same distance from an interior point called the focus and an exterior line called the directrix. Then you could have other polynomials that are of higher degree, so degree 3, degree 4. A polynomial is a function in which all the terms have a variable raised to a whole number power. That's what makes a formula a polynomial. So lines are actually a type of polynomial. Parabolas, as I said, are a type of polynomial of degree 2. But any expression in which the variables are raised to whole number powers fits into the category of polynomials. And then we had exponential functions, and an exponential function means your variable is in an exponent. The most basic form is y equals a leading coefficient times your base raised to that variable exponent. We also talked about how all functions have inverses, and the inverses are reflections of each other about the line y equals x. So shown is x cubed, and its inverse the cube root of x. So all of the root functions are inverses of the polynomial terms. Logarithms are the inverses of exponential functions. But then you can also have functions that really don't fit in any category. Here we have data about the COVID cases and the ICU and hospital usage during the COVID epidemic, and that set of data is certainly making a curve that we can see and define. It doesn't fit any of these specific forms, but you could estimate it by making a combination and applying the transformation ideas that we're going to learn in this video. I would like to mention that wave functions are also a very important set of functions. A lot of phenomena are modeled by waves. In college algebra, we don't necessarily include the wave functions as part of our library of functions, but the very next class that most of you will be taking includes these wave functions. They go by cosine and sine. They're actually really both the same wave, just shifted from one another, and we are going to learn about how to shift functions horizontally. So any sine wave can be rewritten as a cosine wave with a horizontal shift, and any cosine wave can be rewritten as a sine wave with a horizontal shift. But a lot of the transformations that we're going to talk about actually are illustrated very well with wave functions. So as you are practicing, you may want to experiment or play around with the wave functions, because you may see the effect of the transformations illustrated very clearly with these wave functions. The first translation that we're going to talk about is a horizontal translation. We'll illustrate it with a simple parabola. Again, parabolas are polynomials of degree 2. So the most basic parabola is the simple equation y equals x squared. And the graph of it has a vertex at the origin 0, 0. And if you plug in 1, 1 squared is 1. If you plug in 2, 2 squared is 4. Or if you plug in 3, 3 squared is 9, etc. And it doesn't matter whether your values are positive or negative. If I square negative 2, I still get positive 4. If I square negative 3, I still get positive 9. So notice we have this nice symmetry about the y-axis because you get the same outputs for positive values of x as negative values of x. Now, if in the square I put the expression x minus 4 inside the square, note to make that expression equal 0, I would have to plug in positive 4. So that vertex, that center point, now gets shifted over to positive 4. So the vertex, instead of being at the origin, has now been shifted to the right 4 spaces. Again, picture what you need to put in for x to make your core expression equal to 0. And that is explaining to you how the graph is shifted. So once again, if I plug positive 4 in for x, 4 minus 4 would be 0, hence creating that vertex point 0 squared. Now consider if inside the square you replaced x with x plus 4. In order to get that expression equal to 0, I would need to plug negative 4 in for x. Negative 4 plus 4 gives you 0, hence that vertex point of 0 squared gets shifted to the left 4 spaces to negative 4. So x plus 4 shifted the parabola to the left 4 spaces. X minus 4 shifted the parabola to the right 4 spaces. Again, focus on what value is going to make your core function equal to 0, and that is telling you where you're shifting the graph, or how many spaces you are shifting the graph horizontally. In this case, 4 spaces, but to the left, because I need a negative 4 plugged in for x to get the core expression equal to 0. Let us look at another example of horizontal translation, this time with an exponential function. We have the function y equals 5 times 2 to the x. That is our base function. If for the variable x I replace x minus 2, notice I would need to plug 2 in for x for that exponent to equal 0. So the graph is shifted 2 spaces right, so the point 0.5 is now shifted to the point 2.5. So notice on the original function, 5 times 2 to the x, when 0 is plugged in for x, you get 5 times 2 to the 0. Anything to the 0 power is 1, so you get 5 times 1, or 5. So on the original graph, when 0 is plugged in for x, you get 5 out. And notice for our basic exponential functions, that leading coefficient tells us our y-intercept, so we can kind of see that. But if you replace x with x minus 2, that leading coefficient is not telling us our y-intercept, because the graph gets shifted, in this case to the right, 2 spaces. So once again, look at what needs to be plugged in for x to make the core expression 0. So 2 to the 0, I would need to plug positive 2 in, hence I'm going to shift the graph 2 spaces to the right. If instead of x minus 2, I plug x plus 2 into the exponent, for the exponent, the core part of the function, to equal 0, I would need to plug negative 2 in for x. Negative 2 plus 2 would be 0. So the graph of 5 times 2 to the x plus 2 shifts left 2 spaces, because I would need to shift to negative 2 to get that core exponent equal to 0. So the y-intercept value of 0.5 shifts to the left 2 spaces to the point negative 2, 5. Again, look at what needs to be plugged in for x to make the core expression, variable expression, equal to 0. In this case, it was negative 2. So the graph goes negative 2, or 2 spaces to the left. Here's another example with the square root function. So the basic square root function starts at the origin 0, 0. Remember, in the set of real numbers, even roots are not defined for negative values. So this function actually has a starting point at 0, 0, and then it goes on to the right from there. If inside the square root I replace x minus 8, that graph is then going to be shifted to the right 8 spaces because I would need to plug positive 8 in for x so that the expression x minus 8 would equal 0. So the point 0, 0, that beginning point, is now shifted 8 spaces to the right, and the beginning point is now 8, 0. All of the other points also get shifted to the right 8 spaces, but the one that kind of stands out the most clearly is that beginning point, 0, 0 getting shifted to 8, 0. Again, 8 is the value that would make the core expression equal to 0. If inside the square root we instead replace with x plus 8, I will shift to the left 8 spaces. So negative 8 plus 8 would be 0. So I need to plug negative 8 in for x in order to get the core expression equal to 0. So the beginning point 0, 0 gets shifted left 8 spaces to negative 8, 0. Again, the negative 8 is the number that makes the core expression equal to 0. Hopefully we've seen enough examples of horizontal translations, and we are now going to look at vertical translations. For vertical translations, you're not replacing inside the main function. Instead, you're adding or subtracting outside the main function. So if we use our basic square root function, but outside the square root I subtract 8, then literally you're going to calculate what the square root of x is, and then you're going to subtract 8. So the entire value is going to go down 8. So notice my beginning point of 0, 0 gets shifted down to the point 0, negative 8. And negative 8 is now the y coordinate, not the x coordinate. So again, note the difference. The minus 8 is outside the main function. So you're literally taking 8 off of the value. Hence, the entire graph goes down 8 spaces. If instead of subtracting 8 from the basic square root, I added 8, then my basic graph is going to be shifted up 8 spaces. So the beginning point of 0, 0 is going to go to the point 0, 8. Again, I'm adding outside the main function, not inside the function. And so basically I'm calculating what the square root of x is, and then I'm adding 8 to it. So all of the values are going to be 8 higher than they would have been had I not added the 8. So adding on the outside shifts it up, subtracting on the outside shifts it down by the number you've added or subtracted. Here is an example applied to log base 10. Again, remember, if you don't write the base for a log function, it's assumed log base 10. If I wanted log base 5, I would have put a subscripted 5. And if I want log base e, we put ln. So log means log base 10. So a basic log function has an x-intercept of 1, 0. If I put 1 into any log function, the output is 0. And that's because any exponential function raised to the 0 is equal to 1. If I add 3.5 to the outside, so take log of x and then add 3.5, I'm going to shift all of the values up 3.5 higher than they would have been had I not added the 3.5. So my 0.10 gets shifted up to 1, 3.5. All of the points get shifted up 3.5. If we take log base 10 of x and I subtract 3.5 from the basic function log of x, the entire graph goes down 3.5 spaces. So my 0.10 is now located at 1, negative 3.5. But all of the points get shifted down 3.5 spaces. So again, you're calculating log of x, and then you're taking 3.5 off of it. Hence, all of the values go down 3.5 spaces. Now, the way you make a graph steeper is by multiplying the main function by a value greater than 1. Think of it in terms of lines. The number that's multiplying x is the slope. And the bigger that number is, the steeper the line is going to be. Well, the same thing occurs with other graphs. It just might be a little harder to see the steepness as it is very directly with a line. So again, we're showing our basic parabola, y equals x squared. and then comparing it with y equals 3.5 times x squared. The 3.5 times x squared is the black graph. On the original parabola, when we plug 2 in, the output is 4. But now that we have 3.5 times x squared, when we plug 2 in, the output is 14. The graph got steeper by a factor of 3.5. And you could see that if you pick any 2 points and figure out the rise versus the run, the horizontal, you're going to get a higher slope with the skinnier parabola than with the slightly wider purple parabola. This method of making a graph steeper applies to any graphs. So if we took the basic exponential function y equals 2 to the x, and you compare it with y equals 5 times 2 to the x, the 5 is making the graph steeper. So notice on the original 2 to the x, when you plug in 0, you get out 1. But on 5 times 2 to the x, when you plug in 0, you get out 5. The graph has gotten steeper. On the original basic 2 to the x, when I plug in 1, I get out 2. But on the steeper 5 times 2 to the x, when I plug in 1, I get out 10. So my y values are increasing more rapidly because of the multiplication by 5, noting that 5 is bigger than 1. Hence, we're going to make the graph steeper. Make a graph less steep, hence flatter. Our leading coefficient is not going to be greater than 1, it will be less than 1. So working again with the basic exponential function y equals 2 to the x, if I multiply 2 to the x by a number less than 1, so 1/3 is a number less than 1. Notice that the purple graph, which is the graph of y equals 1/3 times 2 to the x, it is flatter, it is not as steep. When I plug 0 in for the original function, I get out 1, but now I'm going to get out 1/3 times 1, or 1/3. If I plug 1 into the original, I get out 2 as my output. But now I'm going to get out only 2/3. It's not even equal to 1 yet. So the y values, the outputs I get, are not as high. They're not as dramatic with the flatter graph of 1/3 times 2 to the x as with the basic 2 to the x. Here is another example of making the graph more flat, this time working with a basic cubic function y equals x cubed. And on the original function, when you put in 2 cubed is 8, so my value is 8. If I flattened the function by multiplying with a leading coefficient less than 1, so y equals 0.25 times x cubed, the 0.25 is going to make the graph less steep or more flat. Notice now when I plug in 2, I only get out 2. So my y values are lower and not as extreme. I have flattened the graph. Now, you may hear this called a vertical shrink. When you make it steeper, it is sometimes called a vertical stretch. But I do see different terminology, so I think it's more important for you to understand the overall effect. So multiplying by a value greater than 1 is going to stretch the graph, make it steeper. Multiplying by a coefficient less than 1 is going to flatten the graph and make it less extreme. When you multiply any function with a leading coefficient of -1, the graph flips upside down. The values that were positive are now negative, and the values that were negative are now positive. Here we've used the basic function y equals x cubed, and we are comparing it with y equals -1 times x cubed. So on the original function, when you plug in 2, you get out 8. Now, when you plug in 2, you get out -8. On the original function, when you plugged in -2, you got out -8. But now, when you plug in -2, you're going to get out +8, and so forth. The only point that is unchanged is that inflection point at the origin, 0, 0. Here's another example of a reflection about the x-axis, hence we're flipping the graph upside down. We're using the basic function y equals the square root of x. So when you plug in 4, the square root of 4 is 2. But if I multiply the function by -1, then the 2 becomes the opposite, or -2. That happens with all of the points. All of the points get reflected about the x-axis and become the opposite of what they would have been had I not multiplied by the -1. You can see examples of a lot of our transformations in real phenomena. Here we have the VIX, or the volatility index, which is a measure used by traders to measure the level of fear in the stock market. And against it is the price of a stock called Atmel. Notice that Atmel's performance is nearly the opposite of what the volatility index is. There's a little section in the middle where they're not quite reverses of each other, but for the most part, the blue graph, which is modeling Atmel's value, is the reflection of the volatility index. So if you graphed Atmel and you graphed VIX, it would be pretty close to having one just be -1 times the other. Absolute value is a special case of reflection. It's a special case in that when you take the absolute value of something, you are reporting back the distance of that value from 0. If a value is already positive, then the absolute value is just the value of the number. So the absolute value of 5 is still 5. But if a value is negative, the absolute value is the opposite. So when you take the absolute value, any negative values are going to get reflected about the x-axis, but positive values will stay put. Here we're going to apply this to a wave because the wave nicely waves above and below the x-axis. So sometimes it's positive, sometimes it's negative. When I take the absolute value of the cosine wave, the sections of the wave that were negative get reflected up and become positive, but the sections that were already positive, they're going to just stay in place. So the absolute value of cosine of x turns into a series of humps, all of them above the x-axis, well, except for where the wave is actually 0, is still going to stay 0 because the absolute value of 0 is 0. So where we're hitting the x-axis, those points stay fixed. When you're above the x-axis, those points stay fixed, but the values that were below the x-axis get reflected up above the x-axis. Another nice example of what happens when you take the absolute value of a function. Here we have a parabola in which the vertex is at x equals 0, y equals -4. So there's a section of y values that are negative around the vertex. If I take the absolute value of that parabola, the arms on both the left and the right that have positive y values, they stay fixed, and the zeros stay fixed. But the little section that was below the x-axis, it gets reflected up above the x-axis, and you get these wings with the hump in the middle, and the hump is where the vertex would have been, but that section gets reflected up to make the values positive. The more you understand about functions, their graphs, and transformations, the more you can model any kind of data. Now this data is a bit irregular, but you could actually come up with a fairly decent function smoothing it out, and it would be a wave function in which the absolute value gets applied to the wave function and then added to some other function, maybe a parabola or an exponential function. So if you combined a parabola or a decreasing exponential function with a wave added to it in which the absolute value of the wave has been taken, you would get a pretty nice smoothing out of this curve about the crime data in St. Louis City and County. Now, if you wanted to reflect about the y-axis rather than the x-axis, you're still going to multiply by -1, but this time you're going to multiply the input by -1, not the outside function. So take the square root of x. Notice when I plug in 0, I get out 0. When I plug in 4, I get out 2. When I plug in 9, I get out 3, etc. If we make the function y equals the square root of -1 times x, Now when I plug in -4 for x, I get +4, and the square root of +4 is 2. My entire graph gets reflected around the y-axis, and so all the values of the function are now in the negative side of the x-axis. Notice the beginning point 0 stays where it is because -0 is still 0. Here is another example reflecting about the y-axis. We're working with y equals x cubed, and we are multiplying the input by -1. So notice now when I plug in -2, I have -1 times -2 is +2, and +2 cubed is 8. So we're showing the reflection of the point 2,8 about the y-axis to the point -2,8. Now with these odd polynomial terms, multiplying the input by -1 is essentially the same as multiplying the output by -1. If you distribute the power 3, you're going to get -1 cubed times x cubed, which is going to give you the same expression or an equivalent expression, y equals -x cubed. But if the input is like the square root or a square or some of our other functions, you can more dramatically see that we're truly reflecting about the y-axis, and it's not a combination of either reflecting about y or x. In this case, the function could be considered a horizontal reflection about y or a vertical reflection about x. The way we have it is written as a horizontal reflection about the y-axis. The next transformation we're going to talk about is a horizontal stretch, in which we multiply the input by a value greater than 1. In this case, we make the graph faster. That is, we reach y values at a faster clip as we go down the x-axis plugging in x values. For example, if we take natural log of x, if you plug 1 in for x, you get out 0 for y. Before that, your y values are negative. But now that we've multiplied the input by 4, and 4 is greater than 1, I reach 0 by the time I plug in 0.25. On the original graph, in order to get a y value of 1.6, I had to go all the way down the x-axis to 5. Now, when I plug in 1.25, I'm already at a y value of 1.6. So that's what I mean by you make the graph faster. You reach y values at a higher level more quickly as you go down the x-axis. Wave functions are an excellent example of seeing a horizontal stretch. Here we have the basic wave cosine of x. Then we take cosine of 3x. I'm multiplying the input by 3. Notice the green graph has now been sped up. I am getting 3 waves completed in the same amount of x-axis as I did with the plain basic y equals cosine of x. So I have sped up the graph to be 3 times quicker than. Waves are an excellent example to see a horizontal stretch and how it makes the graph faster. Here we have a basic cosine wave. If I compare it with cosine of 3x, notice cosine of 3x, which is the purple graph, I am completing 3 waves in the same amount of x-axis as the slower green wave. So literally, we are speeding up the graph. We're speeding up the wave by multiplying the input by 3. And I am getting actually 3 complete waves in the same amount of space that I got 1 wave before. Now to make a graph more slow, we call that a horizontal shrink. We multiply the input by a value less than 1 rather than a value greater than 1. So here, once again, we have our cosine wave because waves illustrate this issue very clearly. If I multiply x by 1/3, notice 1/3 is less than 1, my wave gets slowed down. I'm actually only completing 1/3 of a wave in the same amount of x-axis space that I completed 1 full wave. So by multiplying the input by 1/3, I've slowed the pace of the wave down to only 1/3 of the original pace. Now, a lot of graphs have several of these translations all put together. So putting it all together, we have an example here of a parabola. The vertex of our parabola has been shifted from 0, 0 to 7, 2. The vertex has been shifted to the right 7 and up 2. Notice inside the main function, we have replaced x with x minus 7. I would now have to plug 7 in for x for that main part of the function to equal 0. Hence, the graph gets shifted 7 spaces to the right. Now, outside the main function, we have added 2. And so you calculate the function and then you add 2. All the values are going to go up 2. So the vertex goes from 0, 0 to 7, 2. Now the 2.5 makes the graph steeper. So notice the graph looks skinnier because it's actually steeper than the original basic parabola. Notice 2.5 is bigger than 1, so I'm multiplying by a value bigger than 1, making the graph skinnier or steeper. Here's an example in which we've combined a vertical shrink and a reflection about the y-axis. If you look at our basic y equals natural log of x graph, the graph of our translated function, y equals 1/2 ln of negative x, the 1/2 has made the graph flatter. It's less steep than the original natural log function, and the graph has been reflected horizontally about the y-axis. So the graph is now over in the negative values of x versus having been in the positive values of x. We mentioned earlier that a lot of phenomenon does not necessarily fit nicely any of our exact library of functions. But if we understand enough about the library of functions and our graph transformations, we can at least estimate some of these irregular curves. So here again, we're looking at the crime data from St. Louis City and County. We're going to work on the property crime data. So notice that it's a series of humps with the crime becoming worse in the middle of the year in the summertime and less during the winter months. We're going to apply an absolute value of a wave and add it to a decreasing exponential function, and it actually patterns this data pretty closely. So our base function is an exponential function with a leading coefficient of 4,370. So we have 4,370 times e, and it's a decreasing exponential function, so the coefficient in the exponent is negative 0.0743 times x. That's our base function. To that, we're adding the absolute value of a cosine wave. The amplitude of the cosine wave is 3,000, and then we're speeding up the wave by multiplying the input by pi, and pi is bigger than 1, so we're speeding up the wave, and then we're shifting it to the right by 0.5. So cosine waves actually start normally at a maximum. So there's a maximum in this data at 0.5. Hence, that's why I've shifted the data to 0.5. So notice when I add the absolute value of a wave to this decreasing exponential function, I get a pattern that models the property crime data fairly closely. It's not going to be perfect, but data that is modeled on real-world phenomena rarely is perfect, but instead we try to smooth it out to get a general estimate. Here's another example of trying to model some real data. We have ounces of coffee drunk and the CCR, which is a value related to your heart health called the coronary calcium ratio, and a lower value of the coronary calcium ratio is associated with a lower risk of heart disease. Notice that at first, if you drink lower amounts of coffee, your CCR seems to be higher, and if you drink more coffee, the CCR value actually decreases, but only to some point, and then your CCR level starts to increase as you drink more coffee. So there seems to be kind of a sweet spot in terms of the amount of coffee that's actually a healthy amount to consume. This data pretty closely fits a basic parabola in which the vertex is at 27 for X and 0.605 for Y. So using that as the vertex, we're going to shift the graph to the right 27, hence inside the square we're going to write X minus 27. That'll shift the graph to the right 27, giving us a vertex at that location. And then we're going to shift the graph up 0.605. So we're adding to the outside of the function 0.605. Now to finish off the formula, we need at least one other point. So we have the point 0.779. We can plug that point into the formula we've obtained so far, and it'll help us figure out what that leading coefficient needs to be. Okay, so we've taken our basic parabola of x squared, we've shifted it to the right by subtracting 27 inside the square, and we've shifted it up by 0.605 by adding 0.605 outside the square. Now I'm going to plug in 0 for x and 0.779 for y, and then I can solve that equation for a, giving us our leading coefficient. 0 minus 27 squared is equal to 729, and then subtracting 0.605 from both sides gives us 0.174. That then is equal to a times 729, divide by 729, and that gives us a leading coefficient that's approximately 0.000239. So the parabola has been made very, very flat by a very, very small leading coefficient of 0.000239. And if you did have the full set of data, you would see that this parabola with a very, very small leading coefficient that's flattening the graph and then shifted right to an x value of 27 and up by 0.605, it models this CCR data very closely. So again, the ideal amount of coffee, according to this study, again, we're just pointing it out, it was according to this study, but it was a legitimate medical study, seems to be about 27 ounces of coffee. The more familiar you are with the various library of functions and how to work with the graph translations, the more you'll be able to model data. So